later. Lock in your answers. I have. Good morning, everyone. I'm seeing a lot of good stuff up there. A couple of places I would definitely be a fan of, and I will tell you in just a moment of those couple of places. Mrs. Larkin laughs at me every time, but that's all right. That's all right. All right, let's go ahead and get started on what we have here. So let's look at our content question really fast. So looking at point A here, we know that point A is a roller coaster at its highest point. So we're talking about the top of the hill and is at rest at 0 meters per second. That means no movement whatsoever. If I have no movement whatsoever and I have the highest height, what type of energy do I have? Let me know in the chat box. What type of energy do I have? Do I have kinetic or do I have potential energy? So let me know in the chat box. Excellent. I'm seeing some answers fly up there. Potential. Perfect. 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 Good job. So yeah, I'm talking about potential energy. I have no movement whatsoever. So if I have no movement, then I do not need to have kinetic energy in my problem. I can just focus in on my potential energy at point A. But looking at point B here, my roller coaster is at its lowest point, so there is no height whatsoever, but I'm at my fastest velocity. So I'm at my fastest motion here. So if I'm at my fastest motion, am I talking about kinetic or potential energy at this particular point A, or point B, excuse me. Kinetic, Regine, awesome. Sally, awesome. Let's get some more answers up there. Participation is a big deal, folks. Good, excellent. Lisa's got an answer, Andres. So if I have no potential energy at point B, so I have just now potential energy for point A equaling kinetic energy for point B. So I can have my equation, let me pop this up here. I have potential energy, and I'm just going to put a lowercase a, even though I need to be a subscript. Potential energy for point A equaling kinetic energy for point B. Okay, so what that's telling me is that my potential energy is then transferred to my kinetic energy as the particular car or roller coaster, as the roller coaster goes down in the hill. So with that being said, keep this in mind because we will be working with these numbers or this a little bit later. Looking at our social, what is your dream vacation? I love it. Paris and Romania, those are some beautiful places. Anywhere with my family, that's super sweet. I love that, Bowen. And taking a train around Europe, I'm mainly Germany though. Let's see who's that, Catherine or Caitlin. Absolutely, I would love to do that. I am not a backpacker, you could say. I mean, there's people that backpack all through Europe. I would not be that. My husband said Europe would be super expensive for us because I cannot go below a 4-star hotel. I don't understand what he's talking about. So looking at this one here, Brisa, Switzerland, my favorite place. I so want to go there. New York or Colorado, love the mountains. Taking a train around to try some best foods, get away from the house a little bit. Yeah. So here's my secret bucket list place to go is I would love to go to Austria, Salzburg, Austria, because I am in love with the movie The Sound of Music. So with that being said, laugh now, forever hold your peace, but I want to go to Salzburg, Austria and run through the hills like Fräulein Maria because I'm in love with that movie. So with that being said, I know Mrs. Larkin can pop up in the chat box where she would like to go. A nice weekend in, now I cannot pronounce this, but a geopark in China. Let's see, who is this from? Regine, awesome. What is that all about? Let us know in the chat box. Japan, Kate or Kalia, awesome. These are some awesome places you guys want to go. You're young, you're ambitious. Go and seek your dreams out in those vacation spots. So let's go ahead and move on there. Is it? I have to look that up. That is so awesome, Regine. Go to the Bahamas. Yep. Isaiah, I would totally go to the Bahamas too. Class Connect sessions are recorded and distributed for learning purposes. Please do not put any personal information or information of others into the chat box. Make sure you're respectful and always participate often and well. And participating is a big thing because we do have a lot of work to do, so we need to work quickly and promptly today. We are in day 24 of our 60-day adventure. We are going to be working on work today with our 3F assignment and obviously our attendance on the end. It is Wednesday, September 23rd, so don't forget. that tomorrow we do not have any science classes, but there is other classes. So don't think that the day off, just no science class time. We don't get to see you tomorrow. With that being said, looking at our unit, we are chugging along. We're working towards the end. We just have to work on some simple machines and so on and so forth. Today what we're going to do is we're going to explain the relationship between energy and work. We're going to define and calculate some work and identify if work is being done and various factors. So let's just see if work is being done. We may think that work is done all the time, but it actually has a calculation and it has a prerequisite or a criteria for actual work to be done. We're going to do this through our 3F assignment, getting an 80% or higher. That's no big deal because I know you guys can do it. So with that being said, you know what I'm going to ask you on this slide. So some of us already have it open. Go ahead and get those assignments open. I'm going to put your links in the chat box. Here you go. Get those assignments open. Give us a green check when you have those assignments open. Let's see some money. Green checks, everybody. Look at Regine is already helping us out. Again, we want to work quickly and promptly today. We have a lot of work to go through, and we want to make sure that we get it done, and get you out on time. All righty. Let's get those green checks. Look at that, Sally's throwing up the money signs. Let's get those green checks on. We have, let's see, we have 30 of us in class. I would want to see more than half of us to get those green checks. Let's get those green checks. And I'm just going to start checking in with people. Angela, green check. Bryant, green check, please. Looking for Haley. Harmony, green check. Ivana, green check. Jose, green check. Kalia, green check. Keon, green check. And I think my camera is stalling some of us, so I'm going to go ahead and just shut it off for a second. Michaela, green check. Moises, green check. Is it still loading, Bryant? No problems. Thanks for letting us know. Green checks all around. Awesome. Nice job, everybody. So let's go ahead and move on. So let's look at our, let's do a little geometry here. And some of you might be like, oh, no. So let's do a little geometry. Looking at the green lines. I want you to all look at the green lines. Tell me, are these green lines parallel, perpendicular, or neither? Lock in your answers. I have your polling tools. Use your polling tools, either A, B, or C. I'm going to give you about 10 seconds to do this. Lock in your answers. Alrighty, I'm seeing those answers being locked in. Nice job, everybody. 2 seconds up. Alrighty, so with that being said, I'm going to publish our results here. So yeah, unanimously, I would agree that our answer is B. It is perpendicular. Now, what does the word perpendicular mean? Well, perpendicular, if you remember in geometry, is when two lines intersect. That means when two lines touch each other, when they cross each other. And usually when they're perpendicular, they are cross each other or touch each other at what we call a 90-degree angle. And you probably have seen this little box somewhere in geometry or in graphing or something like that. That little box indicates to us that it's a 90-degree angle. So being perpendicular, remember, means that they cross, they intersect. Now looking at the blue lines, let me clear these out. Looking at the blue lines over here, what can you tell me? Are these lines parallel, perpendicular, or neither? Lock in your answers using your polling tools, A, B, or C. I'm going to give you another 10 seconds for this. Another 10 seconds. All right, let's go ahead and publish our results here. And yeah, hands down, unanimously, they are what we call parallel lines. Now, remember what we talked about in geometry. Parallel lines mean that they go side by side. They do not cross. They do not touch each other at any point. They are simply side by side. They can be opposite, but as long as they're not touching, then they are parallel. You need to know and understand the difference between perpendicular and parallel, because when we talk about work today, you need to know the word parallel. It will come back to you every slide. If you have a good understanding of that, then you are good to go. All right, let's go ahead and look at what energy and work is.
Beautiful. Okay, so today we're going to talk a little bit about how energy and work are related, and we're going to loop this back in at the end of our session as well. So let's go ahead and define energy. Again, we already know this energy is the ability to do work. So the way that you can think about this is it's kind of like your overall energy that the object actually owns or what the object actually has. So when an object has kinetic energy, that's the energy due to its what? Starts with an M. Tell me in the chat box. Kinetic energy is the energy due to the object's what? All right, we got to go ahead and fill in this blank. Again, starts with an M. Awesome. I have some people typing, looking good. What does the word kinetic mean? No, don't just copy the person above you. What does the word kinetic mean? Thank you, Caitlin. Lisa, it's not due to the object's meter. That doesn't make sense. Yeah, it's due to its movement or motion. Yeah, so kinetic energy is due to the object's movement or motion. Now, potential energy, on the other hand, is due to the object's what? Think about kinetic energy is motion, so potential energy is what? Starts with an H? Yeah, it's due to the object's height. So again, energy is the ability to eventually do work. It is the energy that the object has. Now, work, on the other hand, is defined also using the word energy, which gets a little bit confusing, but just roll with it. It is very hard to define energy and work, and even scientists find it hard to define these really well. So work is when energy is used to actually move the object or change its height. So work is the change in energy. So I know that's confusing. Energy is the ability to do work, whereas work is the change in energy. You're defining them with each other, which isn't great. But think of it this way again, energy is the total energy that the object actually has, whereas work is when you actually do something with that energy. So when you're actually changing the energy, when you're doing something to the object. In the chat box, go ahead and give me a rainbow if that makes sense. It's when you're actually doing something to the object. You're changing its energy. Excellent. All right, let's go ahead and take a look at an example here. So, work occurs when a force on an object causes parallel displacement or movement. This is the definition that we're going to work with today with our equation. So, again, there's that word parallel. Work occurs when we have a force, so there does have to be a force, and there does have to also be a displacement. Another word for displacement is distance. You could also just say distance. Those two words are technically slightly different when we talk about them in physics, but for today's purposes, we can consider them to be identical. So, displacement or distance. So again, force has to happen, meaning, and then a displacement has to happen, meaning the object moves, and then those two things have to be parallel to each other. So there are two ways for things to be parallel. They can be parallel by going in the same direction. So if force goes to the right and displacement goes to the right, for example, those are parallel lines. They could also be going in opposite directions, where force is going to the right and displacement is going to the left. That would actually also be parallel because those lines still don't cross each other. All right, now what this means is that that force can actually change the kinetic energy, because remember we said work is a change in energy. So if you increase or decrease the speed using the force, then that's changing kinetic energy, and that's changing the work, and that is work being done on the object. On the other hand, you can also change the height of the object, which would change its potential energy. Again, anytime we have a change in energy, we're doing work on the object. We're changing the amount of energy that the object actually has. Okay? This is number 1 in your notes. Go ahead and fill in the blank with the word parallel. Give me a green check when you have it saved. You have 30 seconds. Capitalization does not matter, but spelling does. 30 seconds. Go, go, go. Okay, I'm waiting on green checks from Alec, Annabelle, waiting on Jalen B, Jose, Kalia, Keon, Luis, Kayla, Moises. Green checks, please, Timothy. Green checks. Otherwise, we'll go ahead and move you to the check-in room and check in with you in the check-in room. So please go ahead, give us your green check. That way we don't have to say your name 1,000 times because that slows everybody else down and that's not fair to your classmates. All right, looking good. Gonna go ahead and move a couple students who I haven't heard from yet. All right, let me see. Who else have I not heard from yet? All right, looking good, everyone. Perfect. All right, let's go ahead and keep on moving here.
Alrighty, so let's look at what a work equation looks like, because obviously in physics, in order to prove it, we're going to prove it mathematically. So work, remember, is force times displacement. And remember what we said is displacement is distance at this point, okay? Okay, so with that being said, we are talking about displacement only when they're parallel. OMG. There's that word again, parallel. So make sure that you get that in. So let's go ahead and review this equation here. So we're saying work equals force times displacement. Now, in order to understand what we're talking about, here are our units. Units will always help you with your equation, okay? So if it says joules afterwards, then obviously we're talking about work. If it says newtons after it, then we're talking about force. And if it says meters after it, we're talking about displacement or distance, okay? So with that being said, we're going to put this to work with a practice problem. So a person pushes a box 15 meters along the ground using a force of 100 newtons. How much work has been done? So let's first of all annotate this problem here. So when we annotate this problem, we're going to look at first off 15 meters. What is 15 meters going to tell me? Is it going to tell me is it force? Is it going to be displacement? Is it going to be work? Mass isn't one of our options. It is, and for some instance we are calling it distance, but what is that other word that we are using? Okay, yes, it's meters. Good, Caitlin's got it. Rowan's got it. Excellent. Jade Lynn, yes, it is meters. We're talking about meters, where that is the unit, but what does meters equal? Angelo's got it. Lisa's got it. Sally's got it. Yes, Andres, we're talking about displacement. This is our displacement. Okay, it's that special word, displacement, movement or of an object, okay, or distance of a movement of the object. Now, looking at 100 newtons, obviously looking at our units here, 100 newtons, what am I talking about? Am I talking about work or force here? Good, yes, nice. Yes, I am looking at force, okay? This would be force in our problem. So now I have two things here. First of all, I have our force, and what is my number for my force? And I liked what is my number for my force? Good, 100. And let's go ahead and get those naked numbers with our units, because we do not want any naked numbers. It's just good practice when we're talking about numbers, because it could be 100 meters, it could be 100 newtons, it could be 100 joules. We need to make sure we're specific. Beautiful. So it's 100 newtons. Excellent. Now let's look at displacement. What number do I use for displacement? Good. Yes. Love it, everybody. Nice job. 15 meters. Okay. Using those units, because it could be 15 newtons, it could be 15 joules, it could be 15 meters. We want to make sure we're specific. So now I have a simple multiplication problem. 100 times 15. What do I get? Jade Lynn's got an answer. Excellent. Brisa's got an answer. Rowan's got an answer. I love the participation, folks. This is awesome. So yes, I get 1,500 joules of work. So with that being said, this is number 2 in our notes. This is number 2. There are 2 boxes for number 2. You obviously know the first one's going to be our answer, our number. The second one is going to be our units, which is joules with a capital J. Make sure you get that in. I'll give you 30 seconds to lock in your answers, and obviously, what am I going to say after that? Give me a green check when you got these answers saved and locked in. Daniel, it doesn't matter if you use the comma or not. It still means the same thing. It could be 1,500 or 1,500. You're still okay. Alrighty, let's check in with a few people here. Let's check it in. Remember, again, if you're not checking in a quick and prompt manner, you will be sent to the check-in room. So let's not go there. Let's not go there. All right, so with that being said, let's go ahead and just check in. Brisa, I know you're kind of working. Go ahead and give me a green check when you are finished. Looking for Isaiah, Ivana. Green checks, please. Green checks. Thank you, Isaiah. Thank you, Ivana. I saw those green checks flying. Kalia, green checks. Thank you. Luis, green check. Moises, green check. We don't want to keep saying your name all the time. All right, let us move on.
Excellent. Let's go ahead and do an example that's going to be related to our roller coaster, which we'll end with in today's class. So let's go ahead and talk about what is the weight of a 1 kilogram object. Remember that weight is actually a force. It is the force due to gravity, right? So another way to say weight is the force due to gravity. And this force due to gravity is calculated using mass times the acceleration due to gravity. So let's go ahead and annotate this. 1 kilogram, kilograms is the unit for what? Is that the unit for mass or for gravity? Yep, this is going to be our mass. So down here, I'm going to go ahead and plug in 1 kilogram for our mass. Excellent. Now, the acceleration due to gravity, tell me in the chat box our magic number. What is the acceleration due to gravity? And remember, gravity does point downwards. So make sure that number has a sign in front of it. What is the acceleration due to gravity? Our magic number. Yeah, that's going to be negative 9.8. Perfect. Negative 9.8 meters per second squared. Beautiful. And what is 1 times negative 9.8? Yes, it's still going to be negative 9.8. Let's go ahead and put some units on there. We're talking about a force, so what is the force? Units for force. Perfect, Brisa. Excellent. Thank you, Angelo. Yep, newtons, exactly. Thank you, Lisa. Negative 9.8 newtons. There we go. So that being said, if we have an object that weighs negative 9.8 newtons going downwards, what amount of force would I then need to counter that and lift it upwards? So if the object has negative 9.8 newtons going down, what do I need to lift it up? Go ahead, tell me in the chat box. This is not a trick question, all right? This should be pretty easy. If it's negative 9.8 going down, what do I need to do to balance it off and go up? Yeah, we need positive 9.8, exactly. So the force we need for our object is going to be a positive 9.8 newtons going upwards. So that being said, we know the force now that we're going to use on this object. So now we're going to see what is the work done if we use that force on the object and we lift it 0 meters, 0.5 meters, or 1 meter. Let's go ahead and take a look at 0 meters. What should I plug in for the force, F for the force, in the first blank? Again, what is the force that I am lifting the object with? The force that I'm trying to use to do work on the object. 9.8 what? Positive 9.8 what? Newtons, yes. So positive 9.8 newtons. Awesome. And what is the distance that I'm lifting the object in the first scenario? Remember, distance or displacement measured in meters. What is the displacement of the object? Yeah, it's going to be 0 meters. So 9.8 newtons times 0 meters. What is 9.8 times 0? Anything times 0, anything times nothing equals what? Yeah, it equals 0, and this is work. Work is related to energy, so the units for work is also what? The units for work is also J for joules. Yes, so we actually do 0 work in the first scenario, and that should make sense because remember, work requires both a force and a displacement, and they do need to be parallel. So in this instance, there is no displacement, and therefore there is no work. So there's no displacement, and therefore no work. In the chat box, give me a heart if that makes sense, broken heart if it does not. There was no work done here because we didn't move the object. Doesn't matter how sweaty you get trying to lift that object, if you don't lift it, you haven't done the work. Excellent. All right, let's go ahead and try. No, it's not, Daniel. We'll tell you when to do each question. Let's go ahead and try 0.5 meters. So in this case, what is the force that I should plug in for my first blank? Again, we're using the same force to lift the object. So what is the force to lift the object to counter its weight? Yeah, 9.8 newtons, exactly. So 9.8 newtons is being used to lift the object. And what is the displacement of the object in this scenario? What is the displacement of the object in this scenario? Beautiful, yeah, so 0.5 meters, excellent. And let's go ahead and talk about that. So 9.8 times 0.5 meters, what does that equal? What is the work now done on the object? Go ahead, calculate that. Make sure you give me a capital J for the units, capital J. Thank you for joules. Yes, awesome. This is going to be 4.9 joules, 4.9 joules. Now, let's go ahead and think about this last scenario. If I lift the object even higher, what do you think is going to happen to the work that I've done on the object? Will work increase or decrease? Will work increase or decrease if I am lifting it even higher up? If I'm increasing the amount of potential energy it has. Yeah, exactly. So it's getting higher, which means now it has more potential energy, which means I'm increasing the work done. So let's go ahead and calculate it and actually check that that's true. Again, what do I plug in for the force to counteract the weight of the object? Excellent, excellent. I see Lisa in the chat box. I see Regine, I see Greta. Sally, yeah, 9.8 newtons again, multiplied by the displacement. What is the displacement in this last scenario? What is the displacement in the last scenario? Beautiful, 1 meter. And this should be easy mental math. What is 9.8 times 1? Anything times 1 equals, yes, itself, which is 9.8 joules. 9.8 joules, again, because work is a change in energy, and we know energy is also measured in joules. Great job. Let's go ahead and actually do an application to this.
We're going to complete this on our own. So what is the work done on a box that is pushed to the right using 30 newtons if the box moves 7 meters? So we have 30 newtons here. Look at the units. I also have a kind of a diagram here to help you out. So look at this. And then we have also 7 meters. Simple problem here. Go ahead and plug your numbers in. Let me know and lock in your answers. If you do need some help or if you want to check your answers, we're more than happy to. Just go ahead and private chat us. We're already in private chat because our chat is shut off, so you could just grab it. So with that being said, I'm going to give you 1 minute up on the clock. 1 minute. Un minutos. There you go. Here we Answers are looking good. Also, make sure you give us a green check when you are finished. Green check when you are finished. Alrighty, so let's just check in with a few more people. Excellent. You guys are doing an excellent job on this question. Perfect. All right, so let's go ahead and check in with those green checks. I see a lot of green checks out there. So let's go ahead and just double check. Bowen, green check. You're probably still working there. Bryant, Daniel, green check. I'm looking for a green check from Luis, Lydia, Madison, Michaela, Moises, green check. Alrighty, here we go. Let's go ahead and move on. Remember, if you missed this question, you always have the recording this afternoon in order to get it. So now we're going to talk about force, gravity, and work. What does this all mean? Well, when a force is perpendicular, remember what perpendicular means. It's not parallel. Perpendicular are when two lines meet, when they intersect. So these two lines meet together. And to the displacement, but no work is done. So you have to have displacement, you have to have force, and they have to be parallel. If they are perpendicular, there is no work. For example, if a person's applying force vertically, that means up and down against gravity, but is working horizontally, like walking, then there is still no work. A perfect example of this, you'll see it in the next one, so you should get this one correct. If a person is holding a box over their head, we do have force. We have force that we apply. We have force due to gravity. And we do have displacement because the box is moving with us, moving with our bodies. But the thing is they're moving perpendicular, and you'll see that in the diagram on the next slide. Since they are moving perpendicular, there is no work. It has to be parallel. No matter how far that object moves horizontally, it is not parallel and to the applied force, so it is not work. I can move around the room and change directions, but it is perpendicular. It is not parallel. It is not work. Okay, now some of us may think, well, I think Mrs. Holden is work. Nope, it's not work. Let's see it in examples.
All right, Luis, make sure you answer in the private chat because Mrs. Sepulveda and I are trying to help you. So I put a couple questions in there to help guide you along, but I need your response. All right, so let's go ahead and take a look at this. 3 elements are needed in order for work to be done on an object. We need a force on the object, we need a displacement of the object, and that displacement needs to be parallel to the force. So we need to be causing a displacement, and the displacement must be parallel. Again, thinking parallel means that the lines are either going in the same direction or they're going in the opposite direction. As long as they are parallel, that means work is being done. Let's go ahead and take a look at this first example. So this person lifts a box above their head. All right, so they're using a force by the person to lift the box above their head, and then they're walking to the right. So taking a look at this diagram, is there a force? Is there a force? Yes or no? Tell me in the chat box. Yes, there is definitely a force, right? There's the force by the person lifting the box. Great. Now, is there a displacement? Is the object moving? Yeah, the object is also moving, so yes, there's a displacement, perfect. And then lastly, are those two things parallel, right? So if we have displacement going to the right and a force going up, are those two lines parallel to each other? Is the force causing a parallel displacement? Oh no, they are not parallel. So if they are not parallel, is work being done? Yes or no? Say yes work, no work, tell me in the chat box. No, there's actually no work being done here. So again, you can get as sweaty as you like carrying a book around above your head, making your arms tired walking around. If those things aren't parallel to each other, you haven't actually done any new work on the book. You haven't done any work on the book. Let's go ahead and take a look at this example down here. So we have someone pushing on this box and this person right here blocking his movement. Taking a look here, is there a force? Is there a force? Yes, there is definitely a force. He's pushing, right? You can see that force right there. Is the object moving? Is there a displacement? No, there is no displacement. All right, so in that case, it doesn't even matter whether or not they are parallel because there's no displacement for there to be a line for displacement. So therefore, is there work being done? Correct, there is no work being done. Again, if the object doesn't move, doesn't matter how sweaty you get trying to push it, it is not going to have work done on it. All right, last example right here. All right, so we can see this guy, he is being pulled over to the right and he's moving to the right. So is there a force? Yes or no? Is there a force? Yes, there is a force. What about a displacement? Is there a displacement? Yes or no? Yes, there is also displacement. And those two things, are they parallel or perpendicular? Tell me in the chat box, are they parallel or perpendicular? Perfect. Yes, they are parallel. So yes, being parallel, and therefore is their work done? Yes or no? Yes, this one does actually have work being done. Great job. So the most important part here to understand is that in order to find whether or not work is done, you have to have a force and a displacement, and they must be parallel. So always look for the parallel force, the parallel displacement. In the chat box, go ahead, give me a lightning bolt if that makes sense. Lightning bolt if that makes sense. Perfect. All right, everyone. So this is number 4. All right, we're going to go ahead and turn off the chat. All right, so for number 4, it asks which of these forces is causing work to be done on the book. Remember, the most important idea here is that to find work, we need a force, a displacement, and they have to be parallel. So we need to find where is the force and the displacement parallel to each other. So you can see 15 newtons from our normal force, 18 newtons from our applied force, 15 newtons from our force due to gravity, and the object is moving 3 meters to the right. That is the motion of the object. All right, this is going to be number 4. Go ahead and give me a green check when you have number 4 saved. If you need to check in with us, we are in the chat box. Here we go. We'll give you 45 seconds. Excellent. Waiting on a few more green checks. Rowan, I responded to you. Yes, awesome. So if that's the way the book is moving, which force is parallel to that motion? Which force is parallel to the way that the object is moving? Awesome. Waiting on a few more green checks. Bryant, waiting on Haley, Isaiah, Ivana, Jadelyn, Jalen, Kalia, Moises, Luis, I know you're working, and Rowan. Awesome. Good job. Perfect. Thank you, Rowan. Good, good, good. All right, everyone. Looking good. All right. Just waiting on a few more green checks. Haley, Haley, Haley. Ivana, Ivana, Ivana. Green checks, please. Kalia, Kalia. And Moises. Moises, green checks, please, for number 4. All right, Haley, I just answered you in the private chat. Think about which way is the object moving. Tell me which direction is the object moving. Awesome. And so which force is parallel to that? Which of our 3 forces is parallel? Either the same direction or the exact opposite direction. Yes, perfect. All right, looking good. Let's go ahead and move on, everybody. because we are almost out of time here. Perfect. All right, here we go. All right, so go ahead and submit that assignment. I'm going to turn the chat box on and tell me in the chat box, how did we do on the 3F assignments? Awesome, Sally. Awesome, Brisa, Lisa. Andres, great job. Stephen, I can go back to it after class. Just give me a moment. Perfect. All right, so today we talked about energy and work. Let's go ahead and talk really quickly about the project. So we talked about how you can calculate the weight of an object using mass times gravity, and then you can take that force that you would need to lift that weight of the object and multiply it by distance or displacement in order to find work. So we're going to go ahead and apply this to our roller coaster really quickly. How would you calculate work done on a roller coaster to get it to the top of the starting hill? Let's take a look here. Again, what do I calculate the force as? Tell me in the chat box. Remember, what is the force or weight of the object? What's that equation? Go ahead, tell me in the chat box. I have it circled on the board for you in case you forgot. What is the equation for the force due to gravity, the weight of the object that we need to counter to get it to the top of the hill? Excellent. I see Rishane in the chat box. I see Caitlin typing. I need more participation. Again, the longer we take to participate, the longer we have to go into passing period. So make sure you're working quickly. Yeah, exactly. Force due to gravity is mass times gravity. I'm just going to go ahead and put it as G just to make it a little bit easier for us to understand. And then the displacement of our object, in this case, we're trying to get it to the top of the hill. What's it called when you move an object upwards? Instead of displacement, we call it what? When we move an object up, we call that the object's what? Think about how tall you are. That is your what? Starts with an H. Yeah, that's called the object's height. Awesome. So work in this case is mass times gravity times height, but this work equation is actually identical to what other equation that we took a look at? Is it identical to the potential energy equation or the kinetic energy equation that we already learned at the start of the unit? What is it identical to? Awesome. Yeah, it's actually identical to the potential energy. And this should make sense because at the top of the hill, the potential energy is the amount that it has, amount of energy the roller coaster has. All right. Whereas the work is putting in that amount of energy to give that the roller coaster that energy. So work is giving the roller coaster this energy. Okay, so work is that change. So we give the roller coaster its energy, and then the energy that it has is its potential energy at the top. So those two things are actually the same in this instance because at the top of the roller coaster, that is the only energy that the roller coaster actually has. So that's the work we have to put in to give it that amount of energy. In the chat box, go ahead and give me a smiley face if that makes sense. Smiley face if that makes sense. Those two things are actually equal to each other, and you actually already calculated this on slide number 4. Perfect. All right, I'm going to go ahead and paste this up on the board. So the way to calculate the work done on the roller coaster at its starting point is to multiply its mass times gravity times height, which in this instance is actually also equal to its potential energy because that is the change we need to do to get it to that potential energy. So that is our answer. Work equals mgh. W equals mgh. That is the answer. Don't ask me for the answer again. That is the answer. Work equals mgh. You have 1 minute to get that into your attendance discussion. Link is in the chat box, and then we will log students out. Thank you so much, everyone, and goodbye.
Recording stopped.